Hello and welcome to this video for Chemistry 20, the solutions unit. This is the final lesson in this unit where we're going to look at solubility and some definitions of solubility. So first of all, solubility is defined as the amount of solute that will dissolve in a specific quantity of solvent at a given temperature. So for example, sodium chloride at 20 degrees Celsius, when you have a 100 milliliter volume of water, it will hold 36 grams, okay? Now, if you make a solution that does not contain that maximum amount, it is called unsaturated. If you contain a solution that does contain that maximum amount, it is called a saturated solution. And we're going to look at a saturated solution in a little more detail in this lesson, but it's important to note that in order to make a saturated solution, you usually add more than will dissolve so that there's some solid particles at the bottom so that you can ensure that whatever is dissolved in the solution is the maximum amount of that solute it can hold. Now note that it could still be able to dissolve other solutes even if it's saturated for the one solute. Now, a third solution you can have is kind of like you're tricking the solution, and you have something called a supersaturated solution. To make a supersaturated solution, you have to heat up your water so that more solute is soluble, so it'll dissolve more than it would have at a cooler temperature. Now, normally as you cool a solution down, that extra solute that was dissolved crystallizes out and makes the solution look cloudy. But if you do it really carefully, you can fool the solution to keep that solute dissolved, and then it's holding more than it should at that temperature. Okay, supersaturated solutions are cool because you can play with them, you can pour them out, and although they are an aqueous solution, the minute they touch something, they rapidly crystallize and form one big solid chunk. Okay, so this is another way that we can test what type of solution we have. If we add a seed crystal, so like a crystal of a ionic compound, a little solid crystal, because it's like you need a little nucleus for the crystallization to start. So if you add a seed crystal to the solution and it's unsaturated, the seed crystal will just dissolve. The seed crystal, again, just being an ionic solid little crystal. Okay, if the solution was saturated, the seed crystal will just float to the bottom or float on top. I guess depends on the buoyancy, but it usually falls to the bottom and doesn't dissolve. But if it was a supersaturated solution, the seed crystal initializes rapid crystallization, where the whole thing forms one big solid ice crystal, it looks like, but it's one big solid chunk. Now, what about our ranges of solubility? So we talked about this in our lesson about dissolving. In order to make something dissolve, you have to break the bonds of the solute particles. Whenever you break bonds, that is always an endothermic process. You always have to add energy to break bonds. Sorry, sometimes my pen makes these funny lines. When you form bonds between the solute and solvent particles, that process always releases energy and is exothermic. So whether or not the overall process will be endothermic or exothermic relies on these steps. So if it takes, for example, a lot of energy to break the solute bonds apart, then the solute is probably going to be insoluble. Now, when something is insoluble, there still will be a tiny bit of it dissolving, but it's defined as being less than 0.1 grams per 100 mils. Now, if between 0.1 and 1 grams in 100 mils dissolves, it is slightly soluble. And then to be considered fully soluble, it has to be more than 1 gram in 100 milliliters dissolving. Now, there's an exception to this rule, and that's gases, because you can have a large amount of gas. Yes, it's making up a very small mass, right? Because gas particles are really far spread apart. So even though it seems like a small mass is dissolving, it can still be a lot of gas, and therefore gases are still considered soluble. Okay. Let's take a closer look at a saturated solution. So when you have a saturated solution, again, there's some solid crystals at the bottom, solid solute at the bottom, that you purposely add to make sure that the solution is holding the maximum amount dissolved ions as possible, okay? And what happens as you look at the solution, the mass of the undissolved solute at the bottom remains unchanged. But what's actually happening is some of the undissolved particles are dissolving and some of the dissolved particles are crystallizing. And so a saturated solution is said to be at a state of equilibrium because these are happening at equal rates. Okay, the process of dissolving and the reverse process of crystallizing is happening at the same rate. So while one particle crystallizes, another particle dissolves. Okay, now how can we show this in an equation? So first of all, we know that when something's dissolving, if it's soluble ionic, it's going to dissociate. So this is our dissociation equation for an example of copper sulfate. Well, the crystallizing process is the opposite. It is the ions coming back to make the solid crystal. So how we can show this in one equation in our dissociation equation is to use a double arrow. This double arrow shows that the forward process and the reverse process are happening at equal rates. Okay, so if you're asked to show a saturated solution at equilibrium, you would show the following dissociation equation with an equilibrium arrow. And it can be any solute. It doesn't have to be copper sulfate. This is just an example. Okay? Now, what affects solubility? So, temperature will affect solubility, but it will affect the solubility of solutes differently depending on their state. So when we're making a solution, usually our solvent is water. So we're trying to think of how to make the particles fit amongst water molecules. So make it almost become like a liquid like the water is. When you have a solid, you have to break the bonds of the solute so that the particles can spread further apart in order to mix with the liquid. Okay, so that means at higher temperatures, there's more energy for that to happen. So with a solid solute, which all ionic compounds, by the way, are solid before they're in water, as you increase the temperature of them, their solubility will also increase. Now, there's always exceptions, but the general rule is when you have a solid solute, if you increase the temperature, you increase the solubility. But what about a liquid? A liquid is actually already at the phase that it needs to be in to mix with the rest of the water you're dissolving in. So extra energy is not even needed, and it actually doesn't even affect the solubility. So when you have a liquid, which would be a molecular compound, the solubility is not usually affected by temperature. Last is gases. In order to make a gas dissolve in a liquid, it actually has to lose energy because the gas particles are freely moving. You're trying to slow them down and force them to slow down into a slower phase, which is liquid. Okay? So increasing the temperature of them actually makes them harder to dissolve. So the solubility of a gas is actually inverse. As you increase the temperature, the solubility decreases. Now, what else can affect our solubility? That is pressure. And pressure will only affect the solubility of a gas, not a solid or liquid. And again, if you're thinking about forcing gas molecules to slow down and fit within liquid molecules like water, if we increase the pressure, that forces them to slow down and mix in with the liquid particles. So pressure will increase the solubility of a gas when you increase the pressure. Okay. The last thing we have to look at is something called molar solubility. If you're ever given the solubility of a compound, so let's say you're told the solubility of hydrogen chloride is 46.5 grams per 100 mils at 25 degrees Celsius. And you're asked to find the molar solubility. All it means is convert that into a concentration in moles per liter. Okay? So what you're going to do, basically the solubility tells you all the information you need. This is my mass. This converted into liters will be my volume. Okay? Temperature is irrelevant. So in order to find my concentration, I just need to take my moles and divide by my volume. Only little side here is that we don't have the moles. We need to find them with mass over molar mass. So the mass again was 46.5 grams. The molar mass, this is hydrogen chloride, which we treat like it's ionic even though it's molecular. We balance the ion charges and it would be HCl gas. Now when I put this in water, it ionizes and becomes an acid, right? But before it's in water, it's a gas. And so I have 1.01 plus 35.45. So my molar mass is 36.46 grams per mole. So my moles cancel, or my grams, sorry, cancel. 46.5 divided by that molar mass we just calculated gives us a mole amount of 1.275. Remember to leave this unrounded. And now I can find my C by taking that N and dividing by that V in liters, 0.100 liters. So I get a concentration, we call this a molar concentration, of 12.753 so on moles per liter. Now, sig digs. Temperature is irrelevant in this question, okay? So it's not going to affect your sig digs. We're looking at the number of sig digs in the mass and volume that we were given, okay? So that's 3 sig digs. So this will round to 12.8 because we're cutting off a 5 moles per liter. So if you are asked to find molar solubility, it just means take your solubility and convert it into a molar concentration in moles per liter. Now I have another question here that I practice with my students, giving them a solubility curve, okay? This is actually a bunch of solubility curves. It is telling us the solubility in grams per 100 mils of water at different temperatures for different solutes, a whole bunch of different solutes. And these are the types of questions that they'll see in their workbook and on their unit test. Which compound is the most soluble at 20 degrees Celsius? So I go to 20 degrees Celsius and I'm trying to find which one is the highest. That would be the sodium nitrate. Okay, it has the greatest mass, around 90 grams in 100 mils. So that would be the greatest out of everything. Next question, what is the solubility of potassium chloride at 80 degrees Celsius? So this green line is my potassium chloride. I go to 80 degrees Celsius and then I read off the graph what the solubility would be. That would be 50 grams in 100 mils. That's the units again of the solubility. How many grams on this curve for 100 milliliters? Next, it says we are making a 100 milliliter solution of potassium nitrate, that's KNO3, and we want to dissolve 80 grams. So 80 grams per the 100 milliliters, okay? So my graph is telling me per 100 milliliters, so I go to 80 grams in solubility, look at the chart, go down to temperature, and that would be 50 degrees Celsius, okay? The last question that I have on here is, and again, these questions shouldn't really be tricky. You're really just reading off the graph. You don't have to do any calculations. You're just reading the graph, okay? The only time it gets a little trickier is a question like this when it's asking us, first of all, for sodium nitrate, which is this graph here. How much of it will dissolve in 50 milliliters of water at 10 degrees Celsius? Well, at 10 degrees Celsius, when I go up to my graph, I see that 80 grams will dissolve if I have 100 milliliters. Okay? It's asking me for if I have 50. So you could set up a ratio. 80 grams per 100 mils equals X grams over 50 mils. Cross multiply and solve for X. Or you can note that 50 mils is half of the volume, so it would be half of the solubility. It would be 40 grams per 50 mils. Okay? And that's kind of the hardest it gets. Hopefully that helps, and that is it for this lesson. Thank you very much for watching.